what we're going to be talking about today is what we've been doing over the last year or so in terms of taking our high viscosity technology from lab to market. So first of all, a little bit of a journey. January 2023, we released a white paper talking about the theory about how high viscosity could make a difference in terms of the printing industry. And throughout 2023, we sort of launched a number of little teasers out there showing people what our technology could do and some of the applications that it might be useful in. And then November of last year, we had our first ever Xaar Open Day, and we opened the doors to our R&D lab, and a number of you in the audience came to see, and we gave a number of live print demonstrations for how high viscosity inkjet can make a real difference. And a year ago, I stood here and talked through a number of things, but I talked through the results that we'd been finding with our work with Marabou in terms of high viscosity UV ink, and I talked about some of the work that we've been doing with Xaar regarding high viscosity water-based fluids. And we talked about the benefits of those different concepts. We talked about having more pigment in the UV ink, which meant you could get better colour or perhaps use much less ink for the same colour. And we talked about how a high viscosity water-based fluid on a porous media could deliver more colour for the same amount of pigment. So today we're going to talk about what we've been doing over the last year to commercialise those different technologies in a number of different applications and industries. But first of all, I'm going to hand over to Neil, who's going to talk a little bit about the challenges of current inkjet.
Thanks, Karl. So, as we said, we've taken this from the lab to the market, and we wanted to make sure that we were hitting what the market needs. And there's been a reoccurring theme throughout the number of events I've been to over the years regarding inkjet about how inkjet is penetrating into the print market. And we tend to fall around these main four areas. It's about print quality and speed. It turns about the industrial reliability of systems, the fluid performance, what does it actually do on the materials, and then that total cost of ownership. And we get to that point with total cost of ownership where the reason we can't necessarily get into some of these applications is the crossover point between analog and digital is too short. We need to be able to expand what we do with digital, which means then that we can get more penetration into that market. And as most of us in this room are suppliers of some component or other into that market, sell more of our product. And the only way we can do that is to think slightly differently, as it was said first thing this morning, think differently, and come at it from a slightly different direction. So when Karl spoke last year, he mentioned about the work we did with Xaar and corrugate. So the corrugate segment was one that we decided to go and look at first. And we did some trials, and we've invested heavily at Xaar to prove this. And the idea being that they want to be able to use inkjet more, they want brighter colours, and they want to be able to run faster and potentially, also reduce that cost per print. Karl, please. So there's some other benefits around this that we found as well, though, of course. The first is that we can use higher solid content within these inks. If they're more viscous, it means the solids stay in the solution better. You have less of the solids dropping out, which means you have a more stable solution. If you're using the technology that Karl showed last year, you remember that we showed that we can actually get more variations of colour on uncoated media and porous media. This means actually the gamut increases significantly from what you had before to what you can do with high viscosity. We can use less ink. If we're putting less ink, if less ink is being absorbed into the substrate, we can use less to get the same result. And then finally, we can do formulations that allow us to have more functionality within those fluids. That means we no longer have to stay within those traditional print markets. We can now move into more industrial markets where there is additional functionality and requirements that we can never ever meet before. So the whole point of this was that we've realised that we can have brighter print, we can have a faster print, and also we can have a lower cost print in certain applications. So going back to the corrugate, if we think about where we were, Karl, we've done this slide here. So this shows two prints. The one on the right is a standard viscosity 12 CP fluid. On the right is our high viscosity fluid. Now, the one on the right is significantly brighter. However, the GSM of the print is exactly the same. We've got about 10 GSM, 1.9, 1.5 mils of ink per print. Exactly the same amount of inks going down compared to what you're getting out on the other end. So we're getting brighter print, less ink. So what happens though if the customer says, that's great, but I want the same print? Well, we can do that as well. Same quality print, customer has the same. The key is this number on the bottom right-hand side. We're now using only a quarter of the ink that we used in the one on the right. Okay? Same print quality, a quarter of the ink. Now, some of the ink people in the room now at the minute are panicking. But the idea of all of this is to try and grow that penetration into the market, trying to reduce that cost per print. Okay? And what that means is that if this is a very standard graph that a lot of the print houses use, it's a crossover graph that says that if I've got a print job of X, it's going to go on my analog or my digital print. By being able to use high viscosity, it pushes that line to the right, so it gives more opportunity for digital, makes sure that we can be using digital for more jobs, so we get into more industries, we get more customers, we get more machines in the field, and we print more. Okay? But also what this means, as you've seen from the previous two slides, is potentially we can actually remove some of the processes that we use elsewhere. For example, the first slide where we showed the brighter print, for some customers that may mean they no longer have to buy coated board. Those images, and we have them outside, and please come and see them, are on uncoated white board. If that's now good enough, there's a massive cost saving that some of the end users are going to be able to have by not using coated board. Okay? Cool.
Okay, let's talk through some of the industries and applications that we've been helping to commercialise over the last year. So the first one is textiles. We've done quite a lot of work over the last year looking at how this technology gets commercialised within the textile industry, and there's a number of OEMs that we're currently working with. One of the areas that we've been looking at is how we apply this technology to a white ink. So the video is showing a standard viscosity, water-based, pigmented white ink, and those of you familiar with the direct-to-garment industry will know that right now to get a white ink that's opaque enough on a t-shirt, you have to do 12, 14, 16, 18 passes to get the opacity that you really need. Little video there, we stopped after 5 to keep it fairly short. And what you'll see in a second is Aquinox can pass and print a high viscosity water-based ink in a single pass and deliver a whiter print than standard viscosity. And the images on the right-hand side also show an application where we're using Xaar's patented high laydown technology to do single pass white onto pre-treated cotton at speeds of around 65 meters per minute. Single pass, high opaque white. Printing onto cardboard, what an exciting name. So Neil's already talked about some of the work that we've been doing with CMYK colours, where you can get much higher colour gamut on uncoated media. One of the other areas that we've been commercialising over the last year links back to some of the work that Swansea University found in their findings last year. Swansea published an academic article. It's just fairly recently been published. If anyone's interested, just let me know. But the image from the top left-hand side is a snip from some of the work that Swansea did. Swansea took a standard 12 centipoise off-the-shelf corrugate ink and a 50 centipoise conceptual fluid that Xaar had developed. And they did a number of things with those fluids to compare them. But one of the things that they did was they looked at definition. They looked at, if I drip a 12 centipoise fluid onto a piece of brown uncoated board, what happens? And what happens is it spreads and it bleeds. We had some other people talking about it earlier, but it bleeds in an uncontrolled way. If you look at the 12 centipoise droplets of liquids, they're not possible to control in an industrial process. And you look at the 50 centipoise fluid drops and they're very consistent. So where does definition really help? Well, barcode. So you can see some of the work that we've been doing with Aquinox over the last year and commercialising high viscosity fluid with Xaar is looking at using Aquinox to print barcodes. And the image over on the right-hand side is Aquinox printing at 300 meters a minute, 5 meters a second, running us a 3 millimeter throw distance. And you can see the quality of barcode that we're producing on uncoated, non-primed brown cardboard. Next application is advanced manufacturing. Now there's a few areas that we've been commercialising over the last year in terms of advanced manufacturing. I'm going to talk about a couple of those. The first one I'm going to talk about is one that we've openly talked about already. It's the work that we've been doing with Xaar on painting cars with digital print heads. When it comes to car paints have a number of really important functions that they serve. They are the environmental protection for your cars. They are the reasons why we can have warranties on our cars that we do. But they're not possible to jet. They're a wonderful functional fluid, but you can't pour them in a print head and expect to print them. Whereas traditional inkjet, you can pour it in a print head and it works really, really well, but you wouldn't want to drive around in a car that's been coated with them. So we've been working with Xaar to reformulate a digital paint that you can use to coat cars with that does offer environmental protection. And you can see the video here of a solvent-based paint that we've been developing with Xaar. But the other piece of work that we've been doing with Xaar is on water-based paints. And you can see an example here of a water-based paint that we've been developing with Xaar for painting cars from a graphics perspective. So here we're putting patterns on vehicles. And the robot is, I think, a really nice example of something else that Xaar technology enables. Because of our TF technology, the high flow recirculation system, our print heads can survive at the end of robot arms. They can survive pressure variations that you might see within such a system, which means that we can print in any orientation. We can print upside down. And the example on the left-hand side is a car bonnet where we've done multiple sways, single-pass printing with Xaar and the next area of advanced manufacturing that we've been commercializing this year is with electric vehicle battery coatings. Now, for those of you not aware, electric vehicle batteries are metal cylinders or metal rectangles that, with existing technology, get wrapped with a PET film. And that film's there for a number of reasons, but the film really is all about electrical isolation. The problem with the film is that it's a fairly complicated process to wrap a rectangle within a film, but it also starts to cause limitations when the batteries start to get hot, which they do when you charge them. The film starts to laminate, it starts to wrinkle, it causes safety concerns. So right now you have to be really careful with how you charge your battery because the film starts to delaminate. And we've been working over the last few years now with a number of companies who are commercializing digital coating of electric vehicle batteries. And it's all about viscosity. Because when you coat a cylinder cell or a prismatic cell, you have to get a very defined thickness of coating. You have to get the right dielectric properties. You have to go over the sharp edges, and you still need the thickness over the sharp edges. You can't have a watery fluid that is 100 microns thick on the flat surfaces, but 30 microns thin over the sharp edges. That's just not okay. The other benefit of the high viscosity is that it enables you to do high layer thicknesses in a single pass. And again, that's super important in terms of process simplification, lower cost machines, lower cost batteries. Neil mentioned it earlier. And then 3D printing. We've done a lot of work this year in terms of commercializing 3D printing with Xaar technology. The example on the screen is where we are using a Xaar print head to jet a phase change fluid. What's a phase change fluid? Well, phase change fluid is one that at room temperature is a solid, wax in this instance, and the wax gets heated up and it turns to liquid, and we jet it as a liquid, and as it comes out of the print head, it solidifies and forms a solid wax. So we now have Xaar technology operating in commercially available machines around the world, and our technology is running at temperatures up to 75 degrees C. So the print head is basically in an oven, in a hot box, and the fluid circulates and the print head carries on happily. And the benefit to the high viscosity for this application is that our customer has been able to reformulate their wax. So their wax is a stronger fluid, and that's really important for them because it means that they can print very small, fine features without it falling apart and breaking. And that's really important because their application is in creating customized bespoke jewelry, where fine features and details means their products are more premium. Neil.
Thanks, Karl. So, as you can see, high viscosity we've been seeing in a lot of applications in a lot of industries. Now, this is all enabled through the Xaar printhead technology. But we understand, though, that this takes a long time. Some of these projects have been going on for a number of years and are only now beginning to get to that point of being commercially available to end users. So we've looked at how we can provide this to the rest of the industry and how do we go about getting this technology to market as fast as we can. So, as I said, Xaar is a printhead supplier, but we've changed our focus a little bit, Karl, to include the rest of the components that are needed to be able to get people to market faster. Okay. So we have the print heads, which are the robust design, they're designed for high viscosity, and they can cope with those higher temperatures. But we've also then been working with a number of partners for inks and fluids. So these are specially designed inks that we know work in these applications. We have our MagnaJet sister company who can supply fluid systems that are designed for high viscosity. Now, this is an area where we found a big shift in what's available in the market and how well it works. Through a lot of error and trial, we have found that you need a certain type of ink system to be able to manage these, especially when you go down the route of those phase change materials at the higher temperatures. And then finally as well, we've also got the data path partners, the people who are sat in this room today, plus others around the world, who have the electronics available to put those print heads to work. Okay? So in essence, what we're trying to say to you is by using the Xaar high viscosity technology, we can print using less fluid in certain applications. And remember, all this is depending on the application. We can look at printing faster as well. If we can print with less fluid for the same print quality, it means we can print faster. We can achieve better quality. We can reduce energy by not having fluids absorb into the substrates, especially in those such as corrugate and textile. You know, we're looking at more vibrant colours. You can load those inks with more colour. Less is absorbed into the substrates. Again, we get that brighter colour. And also we can try and simplify the processes. We can reduce people's costs. We can try and make inkjet more attractive for more applications and take more jobs out of the analogue system. Okay? Thank you.